Yes, students, in this session, let us discuss about how to establish a condition for one line which is in a symmetric form to lie in a what? Plane. When the plane is given in the form of Cartesian form, say for example, a to x plus b to y plus c to z plus d2 is equal to 0. So therefore, let us consider the equation of a line in a symmetrical form. What's the equation of a line? The equation of a line is x minus x1 by a1, y minus y1 by b1, z minus z1 by c1. Right? To lie in a plane. What's a plane? The plane is given by a to x, b to y, c to z, d2 is equal to 0. You call this as a 1, you call this as a 2. Both are in Cartesian forms. Now, I want to find out the condition for this line to lie in this plane, correct? Now, let us consider the point on this line, any point on this line. Let P of x comma y comma z be a point in the line 1, which implies x minus x1 by a1, y minus y1 by b1, z minus z1 by c1. You take this equal to lambda. Okay, some parameter. Therefore, I can write x minus x1 is equal to a1 lambda, y minus y1 is equal to b1 lambda, z minus z1 is equal to c1 into lambda. Therefore, x is equal to x1 plus a1 into lambda, y is equal to y1 plus b1 into lambda, z is equal to z1 plus c1 into lambda. Therefore, P of x comma y comma z is equal to x1 plus a1 into lambda, y1 plus b1 into lambda, z1 plus c1 into lambda. Right? Got it? Now, this is the point on this line. Now, what is our context? We have to establish a condition such that the line must lie in a plane. So therefore, since this line is also containing this point must also lie on the plane. Which is the plane? A to x plus b to y plus c to z plus d2 is equal to 0. So therefore, now P must lie or must satisfy the plane 2. So therefore, 2 implies a2 into x1 plus a1 lambda. This is b2 into y1 plus b lambda plus c2 into z1 plus c1 lambda plus d2 is equal to 0. So therefore, which implies a2 x1, b2 y1, c2 z1 plus d2. You call plus lambda into a1 a2 b1 b2 c1 c2. For all values of lambda, this must be an identity. Identity in the sense LHS must be equal to RHS, which implies I can write A2X, B2Y1, C2Z1 plus D2 is equal to 0. A1, A2, B1, B2, C1, C2 is equal to 0. Yes, now we have established two conditions for one line to lie in a plane. What is that? First condition is A2X, A2X1, B2Y1, C2Z1 plus D2 is equal to 0, and A1A2 plus B1B2 plus C1C2 is equal to 0. C1C2 is equal to 0. So now how we got? First you select a point on this line, let it be what? With lambda. So therefore cross multiply, I could get as x minus x1 is equal to a1 into lambda. Transfer this x1, x equal to x1 plus a1 lambda, y is equal to y1 plus b1 lambda, z is equal to z1 plus c1 lambda. Therefore, p of x comma y comma z can be taken as x1 plus a1 lambda, y1 plus b1 lambda, z1 plus c1 lambda, right? Now, since p must satisfy the plane to y, condition for a line to lie in a given plane. Therefore, P must satisfy the plane 2. So therefore, A2 into x1 plus a1 lambda, B2 into y1 plus b1 lambda, C2 into z1 plus c1 lambda plus D2 is equal to 0. So therefore, this came written as A2x1 plus B2y1, C2z1 plus D2. Plus lambda into a1a2 plus b1b2 plus c1c2 is equal to 0. So therefore, now a2x1 plus b2y1 c2z1 plus d2 is equal to 0. Next, a1a2 plus b1b2 plus c1c2 is equal to 0. Yes, what is the heading says? One line lies in the what plane? Now the cases arises. What it arises, what it leads to. When the line 1 completely lies in the what plane 2? Completely lies in the plane 2. What is the condition? Next, when the line 1 meets the plane in a unique point, then it must have a unique solution. Then third case arises as when the line 1 is parallel to a plane. Parallel to a plane means it never meets a plane, correct? Then what is the condition? What is the condition? Let us discuss about in detail. Now we have discussed the condition for this. You take this as result 3. Now coming to case 1. As I told, when this line lies in the given plane, when a line lies completely in the plane 1, means every point on this line must satisfy this plane. Therefore, for all values of lambda, it must be an what? Identity. It must be an identity. So therefore, now this is equal to 0, this is equal to 0. So therefore, I can say case 1, when 1 lies completely into, therefore every point on the line must satisfy the plane. So therefore it must be an identity. I can write the same conditions. Then the condition is, that is a2x1 b2y1 is equal to 0, and a1 a2 b1 b2 c1 c2 is equal to 0. These are the condition as we have verified, argued for what? The identity for the different values of lambda. So therefore, when 1 lies completely in the what? 2, these are the conditions. Then let us see what is case 2. Case 2. When 1 meets the 2 in a unique point, then now 3 must have unique solutions. Unique solutions, right? Must have unique solutions. So therefore a1 a2 plus b1 b2 c1 c2 is not equal to 0. Is not equal to 0. Then for case 3, what's a case 3? We discussed in case 1, when 1 lies completely in 2. It must be an identity, both must be equal. Why? Every point on the line must satisfy the plane. When 1 meets the what? 2 in unique point, only one point. This is a plane. A line meets at only one point. Unique solutions. Therefore, a1 a2 plus b1 b2 plus c1 c2 not equal to 0. Coming to case 3, when 1 is parallel to 2, it never meets the what? Plane. So therefore, this is the line, this is the plane. For this plane, this line is parallel. Followed? This is the line. This line is represented by the equation 1. This is represented by equation 2. So therefore, this is plane, this is the line. For this plane, this line is parallel. It is quite obvious. Nevertheless, every plane must have a what? Normal. For this normal, this line will be perpendicular. It is quite obvious. If I take this line as a vector, this normal as a vector, when any two vectors are said to be perpendicular, their dot product is equal to 0. When any two vectors are said to be orthogonal, their dot product is equal to 0. I mean, a bar is equal to a1i plus a2j plus a3k. B bar is equal to b1i plus b2j plus b3k. If two vectors are said to be either perpendicular or orthogonal, a bar dot b bar is equal to 0. Nevertheless, a1 a2, okay, a1 b1 plus a2 b2 plus a3 b3, it all depends upon the is equal to 0. It all depends upon the how the vectors you are going to consider the components. Therefore, now when the 1 is parallel to 2, it is quite obvious this line is perpendicular to the normal. This is a normal, this is a line. So therefore, I can write, so which implies a1 a2 b1 b2 C1, C2. Yes, these are the conditions we established for when one line to lie in a plane. Lying in a plane means three cases arises. One is completely lies inside the plane. Every point on the line must satisfy the plane. Therefore, the condition is equation 3 becomes an identity for all values of lambda. Therefore, these are the two conditions for one line to come lie completely in a plane. When a line is what? Intersecting a plane at one point means it intersects at unique point. Therefore, unique solution. A1, A2 plus B1, B2 plus C1, C2 not equal to 0. If it is parallel, it is perpendicular to the normal. Therefore, A1, A2 plus B1, B2 plus C1, C2 is equal to 0. Let us recall this concept by giving some vivid example as a desired. Yes, let us take roughly one example. X minus 1 by 2, y minus 2 by 3, z minus 3 by 4 is one line. You call this as 1, and a plane 3x minus 4y minus 5z plus 9 is equal to 0. You call it as 2. Yes, compare this line with x minus x1 by a1, y minus y1 by b1, z minus z1 by c1. Followed? Therefore, what is a1, b1, c1? a1, b1, c1 is equal to 2, 3, 4. And x1, y1, z1. P of this point is 1, 2, 3. Next, you compare this plane with a2x, b2y, c2z plus d2 is equal to 0. Therefore, a2, b2, c2 is equal to 3, minus 4, minus 5. Correct? Right? Let us verify. Come on, condition is a1, a2 plus b1, b2, c1, c2 is equal to a1, a2. Yes, now 2 into 3, 6. Next to minus 12, minus 20. Right? So therefore, it is quite obvious not equal to 0. Okay. So therefore, now look here. Let us check. That is a2x1, b2y1, c2z1 plus d2. Okay, is equal to a2x1. Take this point, substitute it in this plane. Come on, this becomes 3 minus 8 minus 15 plus 9. Correct? Okay, now coming this one is, yes, now 12. This is not equal to 0, right? So therefore, what I can write is, look here. Now coming to this line does not lies in a plane. Next comes, now is it one line? The line 1, does it intersect the plane in unique point? Yes. For unique point, we won't verify a2x1 plus b2y1 plus c2z1 plus d1. We verify only for this. Yes, it meets in unique point. So what about, is it line is parallel to the plane? No. Why? Because for when a line is parallel to a plane, certainly a1, a2 plus b1, b2 plus c1, c2 not equal to 0, is equal to 0. So therefore, now here not equal to 0. Hence, this line meets the plane in only one point, unique point. Followed? Now, students, let us recall the concept of one line lies in a plane. Let the equation of a line in a symmetrical form be x minus 2 by 3, y minus 1 by minus 5, z plus 2 by 2. Lie in the plane. What's the plane? X plus 3y minus alpha z plus beta is equal to 0. Then alpha comma beta is equal to dash. Alpha comma beta is equal to dash. Now look here, alpha comma beta is equal to dash. Now what I do is lie in the plane. Yes, the context is you consider this line as a1 y minus y1 by b1 z minus z1 by c1. What's the point? x1 y1 z1 2 1 minus 2. Yes, come on. a1 b1 c1 is equal to 3 minus 5 2. Yes, now what's the plane? The plane is a to x b to y c to z plus d2 is equal to 0. Therefore a2 b2 c2 is equal to 1 3 minus alpha, right? Okay, now coming this one is, what I do is, now first, since now you call this as a 1, you call this as a 2. Since 1 lies in the plane 2, which implies, okay, which implies they have to satisfy two conditions. One is a1 a2 plus b1 b2 plus c1 c2 is equal to 0. Next, a2 x1 plus b2 y1 plus c2 z1 plus d2 is equal to 0. It must be an identity. Both must be equal to 0. So therefore, what I write is, which implies a1 a2 b1 b2 c1 c2 is equal to 0. Next comes about, yes, a2 x1 b2 y1 c2 z1 plus d2 is equal to 0. These are the two conditions that substantiate the what? One line to what? Lie in a plane. So therefore, now what I do is a1 a2, yes, come on, 1 into 3 3. Next, 3 into minus 5. Next, minus 2 alpha is equal to 0. 3 minus 15 is equal to 2 alpha. Therefore, minus 12 is equal to 2 alpha. This and this get cancels. Therefore, alpha is equal to how much? Minus 6. Alpha is equal to minus 6. Then there comes about a2 x1. This is x1 y1 z1. Take this point, substitute here. So therefore, 2 plus 3 plus 2 alpha plus beta is equal to 0. Once again, 2, 1 into 3, 3, minus 2 into minus, plus 2 alpha. In place of z, you are supposed to put minus 2. So therefore, now I can write 5 plus 2 into minus 6 plus beta is equal to 0, minus 12. Therefore, beta is equal to 7. Nevertheless, alpha comma beta is equal to minus 6 comma 7. This is how you can establish the unknowns alpha and beta when one line lies in the plane, or one line meets the plane in a unique point. When one line, unique point, a1 a2 plus b1 b2 c1 c2 not equal to 0. Next, when one line is parallel to a plane, then a1 a2 plus b1 b2 plus c1 c2 is equal to 0. You apply all these conditions in the situation demand. Followed? Students, let us discuss about how to find out the bisector for the two intersecting planes. What it says, the equation of a plane bisecting the angle between two intersecting planes. Now let us consider the two planes. This is This is one plane. So therefore, now you consider, you take a point, this is a bisecting plane. You draw a perpendicular, you take L. You draw a perpendicular, you take this as M. So therefore, this is one plane, this is another plane followed. These are the two intersecting planes. For these two intersecting planes, I want to find out a plane bisecting the angle between the two planes. The context is the angle may be acute, angle may be obtuse. Let us see how to identify the plane is an acute bisector, or plane is an obtuse bisector, or plane containing the origin, or plane not containing the origin. Understood? So therefore, now what I do is, let a1x plus b1y c1z d1 is equal to 0. Now a2x c2z, you call it as 2, right? Okay, these are the two planes. They are intersecting. Now I want to find out the plane bisecting them. Yes, this is the what? Plane bisecting two intersecting planes. In that plane, you consider a point P of x comma y comma z. That point whose position lies in the plane which is bisecting the two intersecting planes. Suddenly, that point P is equidistant from this plane and this plane. So therefore, apply perpendicular distance from the point P to both the planes, and they are equal. Why? Because P will be equidistant from both the planes. The quite a similar concept we come across it in the straight lines. The equation of a straight line which is bisecting the angle between the two straight lines. So therefore, when you take a two straight lines like this, what is that? So this is one line, this is another line. This may be L1, this may be L2, this may be an acute bisector, this may be an obtuse bisector. The same treatment shall also extend it to three-dimensional. Here we focus our attention for two-dimensional, aptly speaking, straight lines. They are of the form a1x plus b1y, c1 is equal to 0, a2x plus b2y plus c2 is equal to 0. Now, if I select a point on this, from this, the perpendicular distance to this line and to this line are always equal. So therefore, equate the perpendicular distances, provided before finding the perpendicular distances from P to both the lines, we have to make the signs of both constants C1 and C2 must be same sign, either both negative or positive. First and foremost thing shall be confined on what? Constants. Understood? Now, coming to this one is, here also, before finding the perpendicular distances, we have to make D1 and D2 must have the same sign. The first and foremost condition is applicable on the constant. Then we go for finding the perpendicular distances. Now let us consider, after now same treatment can also be extended to what? Planes. Now let the proof of this one is very simple. Let P of x comma y comma z be a point on the bisecting plane, which implies P of x comma y comma z is equidistant for both the planes So therefore, now when and also d1 into d2 must be greater than 0. First you have to pick it. Now you take a what? L be the feet of L comma M be the feet of the perpendiculars from P to the two intersecting planes respectively. What is PL? PL is nothing but a perpendicular distance from the point P to the one plane, and PM is a perpendicular distance from the point P to the another plane. So therefore, now PL is equal to PM. PL is equal to PM, where L comma M are the feet of the perpendiculars. So therefore, now I can write, so perpendicular distance, now modulus of A1x, B1y, C1z plus D1 by square root of A1 square, B1 square, C1 square. This is nothing but A2x, B2y, C2z plus D2 by square root of A2 square, B2 square plus C2 square. Why? They are equidistant. Followed? So therefore, now what I do is, yes, you remove the modulus sign. A1x, B1y, C1z plus D1 by square root of A1 square, B1 square, C1 square is equal to plus or minus A2x whole divided by, this is A2 square, B2 square, C2 square. Now, with the plus sign, one bisector, with the minus sign, you are going to get another bisector. So therefore, what are the bisectors? I can write A1x, B1y, C1z plus D1 whole divided by square root of C1z plus D1 A1 square, B1 square, C1 square is equal to plus of A2x, B2y, C2z plus D2 by square root of A2 square, B2 square, C2 square, right? The another bisector is A1x, B1y, C1z plus D1 whole divided by square root of A1 square, B1 square, C1 square is equal to minus of A2x, B2y, C2z whole divided by square root of A2 square, B2 square, C2 square, right? Now, these are the two bisectors we got it with the two opposite signs. Now, we have established how to find out the bisectors. Now the question arises, what? By giving the two planes, how? Like this. It may be 2x plus 3y plus 4z plus 1, or minus x minus y plus z plus 7 is equal to 0. These are the two planes. Find the equation of acute bisector. Or else find the equation of bisector which contains the origin. Next, find the equation of obtuse bisector. How to identify them? Right? Let us discuss about that in detail. Now, coming this one is, we shall verify one condition. What's a condition? The first and foremost thing is, if A1, A2, B1, B2, C1, C2 less than 0. Look here. The sum of the product of the coefficients of x, y, z is a negative, then what is the equation of acute bisector? What's the equation of obtuse bisector? Meanwhile, we can also add another question to its feather, cap of a, feather. Now what is that? I want the equation of a plane containing the origin. In particular, I want to find out the bisector, plane bisector containing the origin is same as acute bisector. So therefore, the equation of an acute bisector, whatever the sign is there, if it is negative, now equation of acute bisector is this by square root is equal to minus this by square root. This is the equation of acute bisector with minus sign. So what is this bracket? In this bracket you fill up this one, this by this. This is same as the bisector contains the origin. Then what is the equation of a bisector? Obtuse bisector. Quite opposite sign. Now I can write equation of obtuse bisector with the plus sign. So therefore, under the umbrella of A1, A2 plus B1, B2 plus C1, C2 less than 0, then the equation of acute bisector is with the minus, whatever the sign is there, same sign comes. Meanwhile, the equation of a bisector contains the origin. Next, what's the equation of bisector, obtuse bisector? Quite opposite to it. Yes, sir. We discussed under A1, A2 plus B1, B2 plus C1, C2 less than 0. Yes, tell me, what about A1, A2 plus B1, B2 plus C1, C2 is greater than 0? Greater than 0. In that case, what I do is, in that case, I take the what? I take condition. If I take this a greater than 0, change this one argument. If A1, A2, now already we discussed about less than 0. Now my context is A1, A2 plus B1, B2 plus C1, C2 greater than 0. For this, whatever the sign is there, quite opposite is acute bisector, right? So therefore, now what I can write is, coming to, for this, obtuse bisector is this, and this is acute bisector. Okay, so therefore the thing is what, come on, that is with what greater than 0, that contains the what, origin. This is all about how to find out the equation of bisector. Equation of bisector containing origin or else acute bisector and obtuse bisector. All these discussions comes under what? D1, D2 greater than 0. Let us apply this concept for an example. Let us consider 2x plus 3y minus z minus 1 is equal to 0, 4x minus y plus z plus 2 is equal to 0. These are the two planes. I want to find out the bisector of plane bisecting these two intersecting planes. Just nothing. First you make what? Either constants both are negative, constant both are positive. What is that? 2x plus 3y minus z minus 1 is equal to 0, minus 4x plus y minus z minus 2. Everybody does plus. I then did what, come on, minus. It makes no difference. Now, first of all, d1 into d2 is greater than 0, correct? Now, equation of plane bisecting the two planes is 2x plus 3y minus z minus 1 by square root of 4 plus 9 plus 1 is equal to modulus of minus 4x plus y minus z minus 2 by square root of 16 plus 2, right? This is how you can find out. So therefore, 2x plus 3y minus z minus 1 by square root of 14. Now this is also minus 4x plus y minus z minus 1. This is nothing but 18. Remove the modulus sign. What's the modulus sign? I can write 2x plus 3y minus z minus 1 by square root of 14 is equal to plus or minus y minus z minus 2 by square root of 18. This is how you can write down. This is the what? Bisectors. With plus sign, I can write, yes, come on, 2x plus 3y minus z by root 14 is equal to minus 4x plus y minus z by root 18. This is 1. The another one is 2x plus 3y minus z by root 14 is equal to minus of minus 4x plus y root 18. This is the answer, right? These are the two bisectors you can find out. Now, sir, one important discussion we have to make it. What is important discussion? This may be an acute bisector, this may be an obtuse bisector, irrespective. Then how to find out, how to identify which is acute bisector, which is obtuse bisector, conceptually. Now, that is, I told A1, A2 plus B1, B2 plus C1, C2 less than 0 or greater than 0 according to that. Less than 0, that's acute, same thing. Or quite opposite is what? Obtuse, correct or not? Now, coming this one is, what I do is, now, if I take this as one plane and one bisector, apply angle between one plane and one bisecting plane. If tan theta is less than 1, then theta is what? Less than 45. Theta is what? Less than 45. So therefore, now the only thing is, the context says, just to apply an angle between one given among the two planes, take one given plane and whatever the bisector you get among any one bisector, you apply the angle. if the angle between first plane and first bisector, or second plane and a first bisector, if it is what, less than 45, that plane is a acute bisector. It is quite obvious other bisector must be what, obtuse. Other bisector must be obtuse. But all this discussion comes under what? D1 and D2. D1 into D2 must be greater than 0. Then you can go for what? Finding the perpendicular distances. The perpendicular distance from any point on a bisecting plane is always equated. Remove the modulus sign, you get plus or minus sign, with plus one bisector with minus another bisector. Then in particularly for objective, how to find out acute bisector and obtuse bisector, we shall discuss.